explanation. All right, so I'm going to start again from this slide. And in this slide, we said last time that we have three different types of log models. We have the linear log, we have the log linear, and we have the log-log model. And always the first term, refers to the y, and the second term refers to the x. So y is linear, x is in log, y is log, x is in linear, or both are in log. And we said last time that log models are actually used if you want to talk about percentages, right? So you want to actually use percentages in your analysis rather than just using dollars and cents and miles and so on. All right, so so let me start from here. So log models, the main use of it is that basically is the conversion, or it converts the changes in variables into percentage, I'm going to write it this way, percentage change. Okay, so when x is small, so when x is just a small number, right? So when x is, for example, just 1 point, okay? So if x is just 1 point, so in this situation, I would be using the log models. So let's say, so when the change in x is small. So you always have this rule, okay? So it basically says that the old value of x plus the change in x, this would give me the new value, right? Which is the old value plus the change. If I subtract it from the old value of x, then I will get the approximation to a percentage change. Okay, so if you even can try this on a calculator, and if you try it on a calculator and you try to just plug in some numbers and you say, okay, what if I have the change in x is equal to 5 units, and suppose that the original value was 100. So if I ask you a question without knowing any econometrics, and if I ask you a question, I say, what is the percentage change in x? All what you need to do is to take 5 over 100 and you multiply it times 100, right? So you would say, okay, the change in x over x is 5 over 100, which is equal to 0.05, and you have it in your mind, okay, it's 5%. Okay, so this is if I multiply it times 100, okay, the change in x is 5%. You can do the same exact thing if you use the rule. So whatever you have here, like this thing, is actually this thing. And I said that this ratio is approximately equal to this subtraction, okay, or this formula. So I can repeat this by saying, okay, it has to be equal to log 100 plus the change minus the original value of 100, right? So that means it has to be the same as log, or natural log 105 minus the natural log of 100. And if you plug it on your calculator, you would find it equal to 0.0487. So whatever I get out of this equation, right, is the same as whatever I get out of this ratio. Why? Because based on this rule, they are approximately the same. Okay, so when I get from the first rule, when I get it as 0.0487, I can easily say, okay, this is approximately equal to whatever I get of 0.05. So based on this topic, which is the log models, log models are used in order to approximate the changes in X into a percentage change. So it converts the changes into percentage change. Whatever you get out of this rule is the same as whatever you get, or approximately equal to whatever you get based on what you already know, which is the change in X over X. So I'm going to write this formula again because this is something very important, and this is what we are going to use multiple times in this topic. So we said that the log of X plus the the change in X minus the natural log of the old X is approximately equal to the change in X over X. And this is our rule that we will use now many times. Okay, so let's start our different types of log models. We said we have a linear log, a log linear, log. So let's start with the first one. What about the linear log model? So it's linear in Y, log in X. So a linear log model would look like this. Yi is equal to beta naught plus beta 1 log xi plus ui. And this I like goes for over like n people or n countries or n whatever the type of cross section that you are using, okay? And now suppose that we consider this one as our equation for y before any changes, okay? So this is the original no change. Now, suppose that I decided to change x and see how it affects y. So if I decided to change x, then if x changes, my new level of x would be x plus the change in x. I still have an error term, I still have an beta 1, beta naught, and anytime x changes, y also is gonna change. Okay, so I wrote it backwards because like it matches what we think about. A change in x brings a change in y. So now let's call this one as equation A, and this is equation B. So if I want to finally know what is the impact of x on y, then it's going to be the equation B minus equation A to get the change in x, the change in y, which is our dependent variable, right? So to get the change in y. So to do that, we basically subtract so when I subtract this part, so I'm gonna have yi will cancel with yi, so I'm left with the change in yi, okay? Now, when I subtract b from a, the beta naught is gonna cancel, okay? Next, when I subtract b from a, I do have a common factor of beta 1. But what I have inside the bracket is log x plus the change in x minus the log of x, right? And of course, the ui would cancel with the ui. And based on what I know, I'm going to call this star because this is important equation or formula that we will use. So based on that, I can always, anytime I see this term, I can remove it and plug in this term. So I can say, okay, the change in yi is equal to beta 1 times the change in x over x. And this is based on equation star or formula star. And now we come to the final point, which is my interest would be, okay, what about the slope? So the slope, which is beta 1, is equal to, just solve for beta 1. So it's going to be the change in yi because of the change or the percentage change in xi. So this is a percentage change in x, okay? And this is what we have for a linear log. So anytime I'm giving you a model and I'm asking you what is the impact of the change in x on y, remember that you will use this formula. So let me give you an example. Or I want you to just make one final note that suppose that, like, look at here, this one here, okay? And suppose that y or x changes by 1 unit, because every time we deal with, like, every time we use 1 unit change, right? We keep saying, okay, it's a small change, so let's say we make it 1 unit. So if x changes by 1 unit, and when I say 1 unit and it is in percent, then it's 1%, okay? So the change in y for a 1% change in x is equal to beta 1 over 100. In other words, you can say that the change in y is equal to beta 1 multiplied times 0.01. Okay, so anytime I have a linear log model, and if I'm asking you a question about, okay, what is the change in y, then change in y is going to be equal to the partial slope attached to the x multiplied times 0.01, and this is for a 1%. What if I ask you 5%? So for the 5%, just, I'm sure that you know that. So if it is 5, just remove this and this, and it's gonna be like, okay, 5% change in x, which is 5 over 100, would bring 0.05 times beta 1 change in y. And I'm sure that you understand, okay, what is the value of beta 1? It's the estimated from theta or the estimated from your regression model. Let me give you an example. So this example, linear log, I have, I need to estimate the factors affecting the minutes of sleeping or sleeping minutes. And we have estimated a model, so this is hat, and the intercept is equal to 5022.82 minus 232.6 1 log total work. I'm gonna write it like this abbreviation, total work. So here we're trying to estimate how the increase in the percentage minutes of work affects the minutes of sleep or sleeping minutes. So this is percent minutes, so x is in percent, y is in linear, is just in minutes. So if I'm giving you a model like that, and I'm asking you, what is the effect of a 1% increase in total work? So this is the total work in minutes, okay? How many minutes you work per day. So a 1% increase in total work would bring 232.6 times 1 over 100, which is 0.01, and this would give you 2.326 minutes. And remember, the sign is negative, right? So that means if a 1% increase in total work, sleeping minutes decrease by 2.326, or you can approximate and say 2.3 minutes. Okay? Notice that when we write our analysis of these types of models, I have to make it very clear that x is in percent, so that's why I'm saying 1%, and y is linear. okay? Because otherwise, when I'm grading your work, I'm like confused whether you understand it actually or not. So you have to make sure that the units of measurement for each variable is very clear and it's written. Now, do you have any questions?
No.
Okay. Now let's go to the next model. And again, I want you to remember that we will still keep our formula, the star formula, okay? So this star formula is very important because we are going to use it in each and every model we are referring to. So let's go to the next. So number 2, log linear model. So a log linear model would be like log y is equal to beta naught plus beta 1 x. Okay, so I don't have any I don't have any nonlinear measurement for x, just in the y plus ui. Now suppose that I change x. So for any change in x, so beta 1, if x changes, right, then y is going to also change, right? So it's going to be the log of y plus the change in y, right? Now, again, this is a and this is b. So b minus a to get the change in the percentage change in y. So if I subtract this part from this part, then it's going to be, okay, log y plus the change in y minus log y equal, beta naught is going to cancel with beta naught. Then I'm going to have beta 1 multiplied times the log, x, right? It's going to go with the x. So I'm left with the beta, I'm left with the change in x, or the delta x. So delta x, okay? Now, again, my interest would be about the change, okay? So based on the formula, I know that I can remove this part and write it this way. Change in y over y is equal to beta 1 change in x, okay? So that means the slope would be beta 1, just solve for beta 1, would be the percentage change in y because of a 1 unit increase in x, whether it's in minutes or dollars or miles or anything, okay? And I want you also to notice that every time I have a model like this and I'm talking about x as linear, my answer has to be in percent, right? So I give you a question, what is the $1 increase in x? Your answer has to be in percent to reflect that y is in percent. So let's see this example. Now I have y is in log of wage. And this is the model we have for today's practice, wages. And then we have an intercept 578 plus 0.067 experience. So this model is trying to find how experience, or the years of experience, so this is in years, this is in percentages, right? So how the additional years of experience would affect the percentage change in wages, okay? It makes sense to say that the additional years of experience would have an increase, or wage would have a percentage increase. Okay, so if the question is if experience increases by 1 unit, and my unit here is years, okay? So if experience increases by 1 year, okay? What happens to the percentage change in experience, okay? So based on what I have here, look at this. Okay, I'm going to just take it on the other side. So this one is saying that the change in y over y is equal to beta 1 change in x. Now, if I want to analyze this in terms of percentages, I want you to remember this is in percent. So if this is 1, then this is 100. If this is 5, then this is also 100. All the time, whatever I have down here is 100, right? So I can actually write it this way. The change in y is equal to beta 1 change in x times y. And I can make it easier and write it this way. The change in y is equal to beta 1 change in x times 100. Or write it, I prefer to write it this way. The change in y is 100 beta 1 change in x. Okay, so now 1 year is here. So this is 1. Beta 1 is here. So this is beta 1. You just multiply it times 100 and get the answer. So the change in y is equal to 100 times 0.067 times 1. Then your answer would be 6.7%. Remember, you have to add the percentage symbol. Okay, so a 1 year increase in experience would bring 6.7% increase in wages because the sign is positive. All right, any question? Next, suppose I have, and this is the easiest one, log. So I have log y is equal to beta naught plus beta 1 log x, okay? So what I have here again is, if you think about it as, again, you're changing x, you can also have the ui, or you can just remove it, it's going to cancel anyway. So any change in x, any change in x, right, would be reflected in a change in y. Okay, now this is like this. Now this is again A, this is again B. Then I want to know what is the change in y. So the change in y would be B minus A. So I'm gonna have on this side the log y plus the change in y minus the log of y equal, these two would cancel, right? I have a common factor, beta 1. Then I have this big bracket of log x plus the change in x minus log x, and the error term is going to cancel. And what I can do is look at the star formula and replace these two. So the star formula would tell me, okay, this part is the change in y over y equal to beta 1 change in x over x. Now, when I have anything in percentages, I know that this is 100 and I know that this is 100. So I can easily remove these two, right? Because they can cancel together. They are the same number. So I can say, okay, the change in y is simply beta 1 change in x. And this brings us back to our normal slope that we know, right? I can just easily read whatever I see in the regression output without multiplying by 100 or dividing by 100, because this is actually what I know. This is what I know about the slope, which is the change in y due to the change in x. And that's why I'm telling you the log-log model is the easiest, because actually it's the same as what we know from how to analyze the slope of any just linear model. So let me give you this example. So this example is an example of the elasticity model, price elasticity of demand, PED. The price elasticity of demand is the most famous log-log model in economics. So it's about the demand for certain good hat. So it's estimated it's equal to 551 minus 67 price. Okay. And let me write here, I forgot the log. So this is log demand and this is log price. So it's a log-log model. I'm telling you, it's easy to analyze this model because I can easily say a 1% increase in price implies 67% drop in demand, right? So I'm telling you it's the easiest because you just take this coefficient and you just add the percentage symbol. You don't have to multiply times 100 as we did with the log linear, and you don't have to divide by 100 when we had it with the linear log. You just take the number, add the percentage symbol. Okay. So you guys have any question?
All good.
Okay, so having covered the three types of log models, the question would be, okay, how these models look like, okay? So I know that in our first introduction to econometrics, we had a linear model, which is, okay, this is y and this is x. This is just a linear model. Now, when we covered the quadratic model, we said that we are adding some nonlinearity and some bends to the model. So the relationship in the quadratic model, for example, which is a type of polynomial models, would be like, okay, like this. Okay, what about the models that we covered today? So this is y linear log in x. This one would actually look like a polynomial. Okay, it looks like, I should say not polynomial, I should say it looks like a quadratic, but it has some flat towards the end, so some flatness towards the end. So it's like this and it gets like more flat. This one I should like have, this one has more of a curvature. Okay, so it might not be very easy to see, but it has like some curvature. Okay, this one like goes like this and gets flat. Next, okay, what about the log? So this one is linear log. This is log linear. The log linear would be like, okay, y is in log x is linear. It's actually very close to a linear shape. And the last one would be, okay, what about the log model? And this is log in x affects log in y, and this one again has some curvature. Okay, so when we either draw these types of models, especially 1, 2, and 3, might not be able exactly to determine which one is the best fit, because they actually look very similar, right? For our eyes, they look very similar to us. unless I can see all the dots and I can actually determine which one is the best fit. But actually this is also a hard job, because it's not that easy to just look at the eye and determine whether they cover all the points or not. But econometrics offers for us a certain test to determine, okay, which one should I use? Is it linear? Is it log linear? Is it quadratic, or linear log, or log log? Because for our eyes, they look the same. So the best answer to that is the following. So how to compare models? Which model is the best fit for our regression? I have so many different types. We said I have linear, I have linear log, I have log linear, I have log log. Okay, and I can keep adding quadratic to the power 3 to the power 4, can add interaction after recovery. So the best answer would be, you can only compare models when the dependent variable, which is y, has the same unit of measurement. So this one, y is linear, right? This one, y is linear, right? This one, y is in log. This one, y is in log. So I can only compare models when the y has the same unit of measurement. So I can only compare the linear with the linear log. I can only compare the log linear with the log log, because they do have the same unit of measurement. And choose the one that has the higher R square, or adjusted R square. Same goes here. Compare between these two models. Choose the one that has the higher adjusted R square, because this would imply that it has a higher explanation to the model. Okay? You can never compare a a linear log with a log linear, because y here is in is linear and this one is in percentages. They cannot be compared. So just before comparing models, just make sure that you do have the same unit of measurement. And in order to do this, you have to actually estimate your model and get the results of the adjusted R square, and then say, okay, this one is better fit for my regression. Okay. All right. So I gave you a couple of examples while I'm explaining. What I'm gonna do next is just to give you like a brief summary of everything I mentioned, because I know like log models is just one of these challenging models. So let me just have one brief summary here. So the model is linear log. So yi equal beta naught plus beta 1 log x plus ui. How can I interpret that? Okay, so the interpretation, so this is the model, this is the interpretation. So a 1% change in x implies change in y. Okay, so you have to take your coefficient and you have to whatever if it is 1%, 1 over 100, if it is 5%, then 5 over 100, and you multiply it times the estimated beta, right, to get the change in y. Number 2, for the log linear, so log y equal beta naught plus beta 1 x plus ui, and here I'm gonna say a 1 unit. When I say unit here, can be dollar, can be cents, can be miles, can be minutes, anything, okay, but not percent. So in x, I am sorry, I 1 unit change in x, a 1 unit change in x, okay. Let me have it clean. So a 1 unit change in x implies 100 beta 1, right? And you add the percentage symbol. Change in y. So you have to multiply times 100, add the percentage symbol. Okay, remember here we didn't add the percentage symbol because y is linear, so I don't need a percentage answer. Last one, the easiest. So log, so log y beta 0 plus beta 1 log x plus ui. So here again, a 1% change in x is associated with beta 1. You just add the percentage sign, change in y. That's it. Okay, so I think it's clear now, and I hope you don't have any confusion about the interpretation of these models. All right. Okay, let's do next. So what we have next